So hey, we're going to graph. It's been a long time since we've graphed. As a matter of fact, we haven't really graphed very much at all this year, right? So now we're going to do some intense graphing. There was a little time where we did some transformations or some. We looked at graphs of quadratics very briefly, right? But other than that, we haven't done a lot. We're going to get into this pretty intensely. Graphing the logarithmic function. Logarithmic, whatever. Hey, just real quick. I'm going to go ahead and graph these using the table. And then I'm going to actually switch over and we're going to use a calculator. Because that's really the fastest way to do it, right? In Algebra 1 or even before that, right? You learned how, way before that, you learned how to plot points, right? So just a refresher, we're going to plot these points. We're going to graph log base 10 and log base 2. And then we'll go ahead and switch it over. All right. So we got this table. I've got a point at 0.625. So x coordinate is 0.0625, which is way close to 0. And then the y coordinate is -1.2. So it's something like that, I guess, possibly close. All right. And then we have another one at 0.125. 0.90, so 0.125 is still going to be pretty close, and then we're at -0.90, so still not too much changing going on. And then we're at 0.25, 0.60, so something like somewhere around there, I'd say. And then we're at 0.5, -0.30, so I don't know, maybe we're close to there, right? And then we have a 0.10, which makes sense, right? Because if I plug 1 in, right, log base 10 of 1 is 0, right? Because 10 to the 0 power is 1. Know what I'm saying? Here, let's point that out. This point right here tells me that log base 10 of 1 equals 0, right? Because and the reason why is because, right, 10 to the 0 power equals 1. Right? That's what that point means right there. It's a special point. Every single logarithmic function goes to that. Always and forever. All right, at 2, we're at 0.30, somewhere around there. At 3, we are at, or no, at 4 rather, we are at 0.60, so I don't know, there maybe. At 8, we are at 0.90, close to 1. Hey, at 10, it should be 1, right? Yep. You guys are awesome. And at 16, we're all the way over to 1.20. So maybe somewhere around there. So we're going to go ahead and connect these dots. And I'm going to point something out to you. This line down here, so really close to 0. It turns out that this gets really close to 0 but never touches it. And then as my x values get larger, my y values continue to increase forever. So what we have here, right, this is the line x equals 0 right there. Yeah, our y-axis is the line x equals 0. I'm going to introduce you to a new word today. And that is an asymptote. It turns out that x equals 0 is an asymptote. An asymptote is a value for which the graph of a function approaches but never touches. So as we plug in values for log base 10 of x, right? We can plug in values as close to 0 as we want, right? And it'll go down to infinity. So what I'm saying is, and why is that? Why is it that there's an asymptote here at x equals 0? Why does the graph of this function not have any values for 0 or lower? Right, yeah, because there's no exponent. I can't put any exponent here that would make this some sort of a negative number, right? There's no value of x that satisfies that, right? And there's no value of x that satisfies that either, right? In other words, you can't take the log of 0, and you can't take the log of a negative number. So that's why this thing approaches 0, comes infinitely close to it, but it never touches it. All right, let's do the next one in green. Let's graph log base 2 of x. So at 0.0625, we are at -4. Whoa. All right. At 0.125, we're at -3. At 0.25, we're at -2. So something like that. At 0.5, we are at -1. And at 1, we're at 0. Okay, we'll always go to that point. At 2, we're at 1. At 4, we're at 2. And then at 8, we're at 3. And all the way out here at 16, we're at 16. 4, let's graph it. And draw the graph, I should say. Plot the points. Alright, there we go. I'm going to go ahead and complete this graph using the graphing calculator. Huh? Let's get this thing out and do it this way. So the first one we had was log base 10, right? Which is easy to do. Log base 10 of x. I can graph that. But these other ones have different bases. So if your calculator has the operating system, you can hit math, go up to log base, and then we can do log base 2 of x. And then the last one that we did not graph by hand was log base 5. Now, don't fret if you do not have this log base function. So there they are. If you don't have the log base function, remember, you can change the base. So let's talk about, again, how to change that base. Graph of all that I do. Oh, all that, no? What's this, Mr. Brother?
You have
I guess I do. All right, so if your calculator does not have that function, as I was saying, don't fret, okay? Because we can write this one in this way, right? I can say that log base 2 of x, remember our change of base formula, it says that I can use that, I can write that as log base 10 by putting that as log base 10 of x over log base 10 of 2, right? And for this one, if I don't have that log base function on my calculator, I can graph it by, instead of graphing log base 5 of x, I'm going to go ahead and graph log base 10 of x over log base 10 of 5. And I'll show you that those two things are the same. Let's go ahead and go back to our handy dandy calculator. And I'm going to put something new here, and it shouldn't change if I put in log base 10. So let's replace, we'll go ahead and replace that log base 2. So log base 10 of x divided by log base 10 of 2, right? This that I just entered is the same thing as log base 2 of x, right? I just did the change of base. So when I hit graph, I should still only have 3 graphs there. Oh, there it is. It's the same, right?
Wow.
So again, if you don't have the log base function, just change the base, and you can graph these on your calculator. All right, well, now that we've graphed them on our calculator, let's answer some fancy questions that Eureka has for us. Yay, fancy questions, Mr. Norman. Okay. What does the graph indicate about the domain of our function? Well, remember, okay, and I think it's been a little while. Since we talked about that, so let's remind you guys that all right. Our domain, remember, is all of our possible x values, right? And our range is all of our possible y values. Little refresher, right? Sometimes we forget these things. So our graph we said it's never going to touch 0. It's never going to be less than 0, right? So we could say that our domain is, we could write that in terms of an inequality, right? And we could say that x, I'm going to say our domain, x has to be greater than 0. We can also say that x is in the interval between 0 and infinity. So those are 2 ways to write our domain. This is not a set of coordinates. It's saying that these are the only values that x can have, right? You remember that if we had a bracket there, it means it includes 0. But we have a parenthesis, and that means that 0 is not included. Are you familiar with that notation? If I had said this, that means that, sorry, my bracket looks terrible. It's despicable. That's bad too. Come on now, you can draw. That means that 0 is included, but it's not the case, right? So this means included. This means not included. But that's not part of our domain anyways, okay? Our domain is actually 0, not including. I just want you to be able to see, this is the notation you see the most, right? The writing it as an inequality. All right. What about the x-intercepts of this graph? Every single logarithm has x-intercepts at x equals 1, right? Because no matter the base, log of 1 is always 0. Because you say, right, whatever that base is to the 0 power is 1. Yeah? I'm going to write this because if I have log, who cares what this base is, right? It doesn't matter. It could be any number, right? Of x. And I should say because for log base b, it's always the case. It doesn't matter what the base is, right? It's always the case that x equals 1. Because we could rewrite that as b to the 0 equals x. And the only solution to this for x is x equals 1. Right? No matter what b is, for this particular equation, x is always going to be equal to 1. No matter what b is. Just anything to the 0 power is 1. Yeah, I'm just showing you a lot of different approaches, a lot of different ways to look at these things. All right, hey, how about the y-intercepts of this graph? Graph? That's corruption. Is that the way dolphins laugh? Because that's cool. There you go. I can't do it. There are none, right? Why? Because x equals 0 and any x less than 0 are undefined. Yeah. All right. Find the coordinates on the point with the graph, on the graph with the y value equal to 1. So what happens? Let's think about it. Well, let's look at our graph first. Let's go ahead and go over here. So I can hit trace on my calculator, and let's see. Do I want to do that one? Log base 10. I'd rather do a different one. So let's look at it. So if I go up, down, it lets me choose between the two functions. Let's do this one. This is technically log base 2 of x, right? I just changed the base. And with my trace function, I can hit my arrow over, and it'll move over x values, and it'll tell me the corresponding y coordinate. And then, oh, I passed it. Well, how about that? I know the answer, right? If you hit with while trace is on, if you just hit Q, enter, it gives you your y value when x equals 2. So that means that my y value is for log base 2 of x, for an x value of 2, my y value is 1. So let's go ahead and write that in terms of an answer. So for f of x equal log base 2 of x, I'm going to write a little weird shorthand way to say that. If we have f of 2, you get. Right, that says that for what? Let's just find the coordinates. So I guess that corresponds to the coordinates. Right? For g of x in this case equal to, oh my bad, this is g of x. I just need to change that to a g. Change that one to a g. Essentially rank it in. Let's do f of x. F of x in this case was, good grief. So f of x was log base 10 of x. So f of what? 10, right? F of 10 is going to give us 1, so that's the coordinates 10, 1. And then for h of x equal to log base 5 of x, f of 5 is going to give us 1. You see the pattern? Which is going to be the coordinates 5, 1. Dang it, I keep writing f's. I want an h here. Sorry. That's supposed to be an h. I'm going to have to erase it with my little eraser. Alright. As x values approach 0, right, so going this way, towards 0, what happens to our y values? Someone said the answer.
0 x y, what happens to the y?
Yeah, what happens to y as x approaches 0?
Maybe closer to like 0? Or negative?
It gets more and more negative, right? Right, as y approaches in negative infinity, x approaches 0. But as x approaches 0, and remember, that arrow means approaches. Always and forever in that, okay? As x approaches 0, it turns out that y is going to approach negative infinity, right? Let's look at that graph. And the best graph that we had to look at is this one, right? On the previous page. Right, this keeps going down all the way to negative infinity. Yeah? And it never stops. X will get infinitesimally close. In other words, right, as close as 1 over infinity to 0. But the closer our x value gets to 1 over infinity, the larger the larger negative value we get for our y value, right? So y just keeps going down, but x is getting closer and closer and closer until it is like 1 over infinity close, right? That's like the smallest number you can imagine. 1 over infinity. Yeah? It's called infinitesimal. 1 over infinity is infinitesimal. All right. Woohoo! Let's keep going. We're doing so much new stuff. New vocabulary, old vocabulary that we haven't seen in a while. All right, as x approaches infinity, what happens to y? It looks like y is going to approach positive infinity, right? Let's look at our graph here. Is there ever a point where this stops increasing? If we look at, say, this graph right here, is there ever a point where it stops increasing? No, there's not, right? It just keeps going forever and ever and ever. And the further out this thing goes for large and very, very large x values, right? Just the y values are just going to get bigger and bigger and bigger. There's going to be more and more and more. Yay! All right. Okay, what's the range of our function then? Let's use our inequality notation. All right? Y doesn't have any constraints on it. Y goes all the way from negative infinity to positive infinity. Right? If we're looking at this value, right? Y keeps going further and further down low, right? And it keeps going higher and higher and higher for different values of x. We could also write that as the interval from negative infinity to infinity. So we could write that as an interval. We can't include infinity at this point because technically, for the math that we have that we're using right now, technically you cannot reach infinity. There is a person that discovered a form of mathematics in the 1960s, and he discovered that indeed you can reach infinity. So, well, we're just going to do it this way. All right. Hey, does it have any relative maxima or minima, right? Our answer is going to be no. Why? Because the graph is always increasing. And now that I said that, let's talk about why that's true. Remember, this guy right here, that's a max, right? In other words, a maximum is where your graph changes from increasing to decreasing, right? There's never a point on the graph of log of x where that happens. Also, a minimum occurs at a point like that, right? Where our graph changes from decreasing to increasing, right? It was decreasing and then it began increasing. This one, it was increasing and then it began decreasing. And if there are no points where either of those cases are occurring, then it must be the case that there are no relative maxima or minima. Cool. We'll leave it at that and we'll finish the rest.